The authors introduce a concise singular value decomposition, SVD, of dual matrices, referred to as CCD-SVD, and its randomized counterpart. Dual numbers and matrices, first introduced by Clifford, have far-reaching applications in robotics, classical mechanics, and computer vision. Building upon previous work on SVD, QR decomposition, UTV decomposition, and rank decomposition of dual matrices, the authors focus on SVD, leveraging techniques from Penistry et al., Guten, Chi et al., and Wei et al. The CCD-SVD is derived using the UTV decomposition technique from Zhou et al. The existence of CCD-SVD is characterized by Theorem 2.1, which states that for a dual matrix A equals as plus I epsilon, with as equals us sigma SV being a compact SVD of as, the CCD-SVD of A exists if and only if I am uses I in VSVs equals ohm times n. This theorem provides a concise SVD of dual matrices, simplifying the singular value matrix as a real matrix. The authors also propose a randomized version of CCD-SVD, which significantly reduces computational cost while maintaining similar accuracy. Theoretical properties and numerical performance of the randomized algorithm are comprehensively analyzed. The paper is structured to present the randomized CCD-SVD, error analysis, experimental results, and concluding remarks. The complex compact dual singular value decomposition, CCD-SVD, of a matrix A is a perturbation of a matrix as with a compact SVD. The CCD-SVD is defined as A equals U sigma V, where U and V have unitary columns, and sigma is a diagonal positive matrix. To compute the CCD-SVD, an algorithm iteratively updates the matrices UI and V using the expressions UI equals IM USU, AIVs sigma 1s plus USP and V equals IUS, sigma 1s Vs sigma SP, sigma 1s. The algorithm starts by decomposing as using a compact SVD and iteratively updates UI and V until a stopping criterion is met. The key difference between CCD-SVD and CD-SVD lies in the fact that sigma is a real matrix in CCD-SVD, reducing the computational cost. Furthermore, a randomized version of the CCD-SVD algorithm is introduced, based on the concept of randomized matrix decomposition. This algorithm takes as input a matrix A, a target rank R, an oversampling parameter P, and a power scheme parameter Q, and outputs the matrices U, V, and sigma. The randomized algorithm involves drawing a random complex matrix omega, constructing a matrix Y0, and iteratively applying a power scheme to reduce the dimensionality of the matrix. The final step involves computing the CCD-SVD of a small dual matrix B and setting U equals Q. This approach enables efficient computation of the CCD-SVD for large matrices. The randomized dual singular value decomposition, RDSVD, is a crucial concept in approximating dual matrices. It emphasizes the importance of capturing the action of as in devising randomized algorithms, as demonstrated by numerical experiments. The error analysis is also noteworthy, introducing the Frobenius norm of dual matrices and presenting theorems on average Frobenius and quasimetric errors. These theorems provide insights into the expected approximation error for the RDSVD method, highlighting the role of the infinite part in low-rank approximation. The authors present a proof for the bound on the error term BARD BLEI, BARD BL2F, a crucial component in the quasimetric definition. This proof leverages the properties of Frobenius norm and unitary matrices as and V's . Specifically, the error term is decomposed into three terms, each bounded using the definitions of chi and q's . The first term, vextend double, vextend double, vextend double, vextend double q asterisk operator psi minus q asterisk operator sway sigma sv asterisk operator s minus q asterisk operator sus sigma sv asterisk operator I, vextend double, vextend double, vextend double, vextend double 2f , is bounded using the unitarity of chi and q's . The second term, vextend double, vextend double q asterisk operator psi minus q asterisk operator sway sigma sv asterisk operator s minus q asterisk operator sus sigma sv asterisk operator I, vextend double 2f backquote, is bounded using the property of Frobenius norm. The authors then utilize the operations in algorithm 3.1 to simplify the expressions and arrive at the final bound for backquote, barred BLEI, barred BL2F backquote. This bound is dependent on the terms backquote by backquote UI backquote is backquote V backquote, and backquote V's backquote, which are related to the singular value decomposition of the matrices involved. The proof builds upon similar ideas presented in Theorem 4.6 in 18, employing the Cauchy-Schwarz inequality to obtain the desired result. The experimental setup for evaluating the performance of the proposed algorithms is outlined, including the baseline CCDS-VD and the evaluation metrics of running time and relative errors. This paper introduces a novel approach to simplifying the computation of dual singular value decomposition, CDS-VD, and its randomized version. The authors propose the randomized CDS-VD, RCDS-VD, algorithm, which significantly reduces computational costs while maintaining accuracy. They also provide theoretical bounds on the approximation errors under Frobenius norm and a quasi-metric. In their experiments, the authors considered dual matrices A equals as plus IO of size 2 meters times M, where the rancor matrices as and I were formed by multiplying B of size 2 meters times R and C of size R times M generated randomly by the MATLAB function RANDN. The rank R, the oversampling parameter P, and the power scheme parameter Q were set to M, 5, 10, and 1, respectively. They implemented CDS-VD, CCDS-VD, RCCDS-VD, and RCCDS-VD with the random dual matrix omega for M equals 2500, 5000, 7500, and 10,000. The numerical results for this experiment are shown in Table 1, where Re1 and Re2 represent the relative errors for the standard part and the infinitesimal part, respectively. It can be seen that CCDS-VD and CDS-VD have similar relative errors, but the running time of the former is a little shorter than that of the latter. The randomized algorithms effectively reduce the computational cost with the accuracy being similar. As for the two randomized algorithms, the one with a random dual matrix performs a little worse in terms of errors and running time. In the second experiment, the authors tested the effect of values of Q on the approximation errors. Two standard images Lena and Pepper with 512 x 512 pixels were first set as element of R 512 x 512 and I element of R 512 x 512, respectively. Then, they generated complex matrices through two-dimensional discrete Fourier transform, which results in the test matrix A equals as plus IO element of District of Columbia 512 x 512. Figure 1 depicts the approximation errors for the standard part and the infinitesimal part for R ranging from 5 to 200 and P equals 4. It can be seen that the power method can indeed improve the accuracy of the algorithm. However, the improvement becomes unremarkable as Q increases. The paper concludes by discussing the effectiveness of the proposed CCDS-VD and the speedup of the randomized algorithm. Future work can explore randomized algorithms for dual quaternions problems. This page presents a comparative analysis of error rates for different power schemes in the context of dual-numbered matrices and their low-rank approximations. The authors compare the CDS-VD, RDS-VD, Q equals 0, RDS-VD, Q equals 1, and RDS-VD, Q equals 2, methods, illustrating the relative errors as a function of target ranks for both the standard part and the infinitesimal part of the dual matrices. The figures depict the relationship between target ranks and relative errors, demonstrating that the RDS-VD method with varying power schemes can significantly reduce the error compared to the CDS-VD method. This suggests that the choice of power scheme is crucial for achieving optimal low-rank approximations in dual-numbered matrices. The reference section includes a list of publications relevant to the field of dual-numbered matrices, kinematics, and singular value decomposition. These studies provide further insights into the methodologies and applications of dual-numbered matrices, offering researchers and stakeholders a comprehensive understanding of the complexities involved in this field. The authors cite relevant works in randomized linear algebra, particularly in the context of matrix decompositions and their applications. They reference a study on randomized dual singular value decomposition for traveling wave identification in the brain, published in the Siam Journal on Matrix Analysis and Applications in 2024. This work builds upon earlier research on QR decomposition of dual matrices and its applications, as well as UTV decomposition of dual matrices and its applications, published in Applied Mathematics Letters and Computational and Applied Mathematics, respectively, in 2024. The authors also acknowledge the contribution of Yu et al. In 2018, who proposed efficient randomized algorithms for fixed precision low-rank matrix approximation, published in the Siam Journal on Matrix Analysis and Applications. These citations demonstrate the authors' awareness of the existing literature on randomized matrix decompositions and their applications in various fields, including neuroscience and signal processing. The proposed method, randomized dual singular value decomposition, is positioned as a novel approach that leverages the strengths of these existing works while addressing their limitations.